Good morning, class. We are looking at the sum and difference formulas in analytic trigonometry. So we looked at trigonometric equations and identities, and we are going to look at the sum and difference formulas. We are going to use sum and difference formulas to find exact values. We're going to use them to establish identities, and we're going to use those formulas involving inverse trig functions, solve trigonometric equations, linear in sine and cosine. So again, reminding you of all the identities that we have seen, starting with the unit circle, periodic function. As you know, all trigonometric functions have a period of 2π with the exception of tangent, which cotangent goes with that. They're all odd functions except cosine and therefore secant. And we have Pythagorean identities, quotient identities, reciprocal identities, and those are important identities to get us started. We are going to look at the sum and difference formulas. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta, and sine of alpha minus beta, basically you replace the beta with negative beta and this becomes negative. For cosine of alpha plus beta, we get cosine alpha cosine beta minus sine alpha sine beta. For cosine of alpha minus beta, we get the same thing with the plus sign here. Tan of alpha plus beta is tan of alpha plus tan of beta over 1 minus tan alpha tan beta. And tan of alpha minus beta, if you replace this with negative beta, it will change the sign. The top becomes tan alpha minus tan beta, and the bottom becomes 1 plus tan alpha tan beta. So what we are going to do now, we are going to start with one of those. In this case specifically, we're going to start with this. We're going to go over the proof, and then we can prove the rest of it. All right, so we are going to prove cosine of alpha minus beta equals cosine of alpha cosine of beta plus sine alpha sine beta. This is one way to prove it. There may be other proofs. You're not responsible for the proof, but if you follow, you're very good at understanding algebra and trigonometry beyond that. We start with two different angles, alpha and beta. Here's the alpha, the bigger one, and here's the beta, the smaller one. So since this is a unit circle, this point has coordinates cosine beta, sine beta, and this one, so this is p sub 1. This p sub 2 has coordinates cosine alpha, sine alpha. Again, this is alpha, the big one. This is beta. And the difference between the large alpha and the small beta is alpha minus beta. And this is the central arc. The central angle, alpha minus beta, subtends this arc. Now, if we establish this distance, but from the x-axis, and this angle of alpha minus beta, if we make it here, then the coordinates for this point, which we are going to call p sub 3, is cosine of alpha minus beta and sine of alpha minus beta. And this point simply has coordinates 1, 0. And the two distances, because both central angles have a measure of alpha minus beta, are the same. So the distance between this point A and this point P sub 3, D stands for distance, is the same as the distance between P1 and P2. Here's P1, here's P2. The reason is very simple. Central angle is identical in both cases, alpha minus beta. So we're going to write the distance formula. Again, I remind you that the distance formula is x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. And you can write that and then you can square it because you working with the squared version is easier. So we are going to write the distance formula for this one, for these 2 points. So the x coordinates would be cosine alpha and cosine beta. Okay, so cosine alpha minus cosine beta is squared. And the y coordinates would be sine alpha and sine beta. So sine alpha minus sine beta is squared. So that's this distance. Okay. For this one, cosine of alpha minus beta minus the x coordinate is 1 here, and then squared sine of alpha minus beta, and the y coordinate is 0 here, minus 0 quantity squared. And as we mentioned, these two are identical simply because they cover the same central angle, namely alpha minus beta. So let me clean this up. So this is equal to this, and it is easier to work with the squared version. So we take this out, and we take this one out too, to work with it. Now we are going to square this. Remember, a minus b quantity squared is a squared minus 2ab plus b squared. So we square this. We square this one. And the same thing for this one. This one, it's sine of alpha minus beta because this goes away. So this is cosine squared minus 2 cosine alpha cosine beta plus cosine squared beta. So this is the first one. This is the second one, sine squared minus 2 sine alpha sine beta plus sine squared beta. And this one is the same as this one, cosine squared of alpha minus beta minus 2 cosine alpha minus beta plus 1, because you are looking at, in essence, a minus 1 quantity squared. And the last piece, of course, is this. So we are just using our algebraic techniques. Now notice cosine squared alpha and sine squared alpha. We put them together. That gives us 1. Cosine squared beta and sine squared beta, we can put them together. That gives us 1. And this 2, we can take the factor of negative 2 out. So the left-hand side, we put these 2 together. These 2, we take a factor of negative 2. And we put these 2 together, meaning now this is 1, and therefore they add up to 2. What about the right side? We can put this one and this one together. This one and this one. When we put them together, cosine squared plus sine squared is 1. This remains, this remains. So what you're looking at, this is 1, this is 1. On the left side, we have 2. This is 1. This is 1. On the right side, we also have 2. On the left side, we write this piece. So the left side is 2 and this piece. On the right side is 2 and this piece. So left-hand side, 1 and 1 is 2, and we just write this. Right-hand side, 1 and 1 is 2, and this piece. The 2's cancel out, the negative 2 cancels out. I hope you see what happens here. If you divide both sides by -2, that's the end of the proof. Divide both sides by -2, and that's the end of the proof. So we proved cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. We proved that. In order to prove this, we are going to replace the beta in the second equation with negative beta. So take a look. Cosine of alpha plus beta is the same as cosine of alpha minus negative beta. So into this formula, beta is replaced with negative beta. So cosine alpha, cosine beta, we're going to replace it with negative beta plus sine alpha, sine negative beta. As you know, cosine is even. So cosine of minus beta is the same as cosine beta. But sine of negative beta, let me write it at the top of it. So this is the same as cosine beta. This is the same as minus sine beta, because sine is an odd function. In fact, all of the trigonometry functions are odd except cosine, and with that goes secant. Therefore, we proved cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. We proved the first one. All right. Now let's use them. We are interested in finding the exact value of cosine of 7 pi over 12. So we want to cut it into two pieces such that both of them are common arcs. 7 pi, it's 3 pi and 4 pi, each one divided by 12. 3 pi over 12 is pi over 4. 4 pi over 12 is pi over 3, and each one is a common arc. So cosine of alpha plus beta is cosine alpha, that means cosine of pi over 4. So this is like alpha, and this is like beta, and this is the formula we are going to use. So cosine of alpha means cosine of pi over 4, cosine of beta means cosine of pi over 3, minus sine of alpha, sine of pi over 4, sine of beta, sine of pi over 3. And we know cosine of pi over 4 and sine of pi over 4 are both square root of 2 over 2. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. Those are all common arcs. The denominator is 4 here. Same thing here. The product of these two is square root of 2. And this one is minus square root of 6. And that's the exact answer. And that's done. So pay attention to the exact answer. We want to come up with cosine of 15 degrees. For now, we can use the sum. Later on, we can use the half. Angle is half of 30. But the sum, clearly 15 is 45 minus 30. We can use that. And again, we're going to use the first formula. This is alpha. This is beta. And we're going to use cosine of alpha minus beta. Cosine alpha, cosine beta. Cosine 45 cosine 30, plus sine 45, sine 30. Again, cosine of 45 and sine of 45, both of them are square root of 2 over 2. Cosine of 30 is square root of 3 over 2, and sine of 30 is 1/2. Both cases, the denominator is 4. This one, the product square root of 6. This one is square root of 2, put a plus sign in between, over 4. And we are done. And note that, by the way, pi over 12 is 15 degrees. It's good to know that. I mention it because if you see that in radians, you should recognize it. And sometimes it's hard. You can go back and forth from radians to degrees and vice versa to make it easy to recognize the value. All right, so we have those, okay, and we want to get to sine of alpha plus beta is sine alpha cosine beta, plus cosine alpha sine beta. Sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. So what we are going to do, we remember previously we discussed the graph showed that the cosine of pi over 2 minus x and sine x, they have the same graph, therefore they are the same function. So let's quickly establish this cosine of pi over 2 minus theta or x or any variable is sine theta, as long as these two are identical. Sine of pi over 2 minus theta is cosine theta. They are co-functions in essence because the angles, they add up to pi over 2. Sine of this is cosine of that. So for the first one, in order to prove that, we stick with this formula. Cosine of alpha, that means cosine of pi over 2. Cosine of beta, that means cosine of theta, plus sine of pi over 2, sine of theta. As you know, cosine of pi over 2 is 0. So this whole thing becomes 0. Sine of pi over 2 is 1, and therefore the answer is sine theta. So we proved the first one. If we let x represent pi over 2 minus theta, then cosine of a pi over 2 minus x is sine x. So cosine of pi over 2 minus theta, instead of theta, we're going to use x. Cosine of pi over 2 minus x, which is pi over 2 minus theta. That is equal to sine x, sine x, sine of pi over 2 minus theta, according to the first one, sine of pi over 2 minus theta. But what if we work on this? It becomes pi over 2 minus pi over 2. Let me write this underneath. This becomes pi over 2 minus pi over 2 plus theta, which becomes cosine theta. And this is x, by the way. Let me just erase it again. This is x, this is x. And then pi over 2 minus pi over 2 cancel each other, minus and minus plus theta. So this is cosine theta. And that's the proof of number 2. Number 2 has been proved. What about the sine? We're going to continue on that thoughts and prove those. So first we establish these two using the sum and difference formulas for cosine. We prove them. Now we want to prove the sine, And first, we're going to write all of those that we have. Cosine of alpha plus beta, cosine of alpha minus beta, cosine of power 2 minus theta is sine, sine of power 2 minus theta equals cosine. So we are going to use one of those to establish this. So sine of alpha plus beta, we are interested in. And if we assume this is x, if this is x, then this is sine of pi over 2 minus alpha plus beta. Sine of alpha plus beta is the same as cosine of pi over 2 minus alpha plus beta. We are assuming this is x. So class, if this is x, if this is x, this is x, x can be theta, or x can be alpha plus beta, anything you want it to be. So whatever this value is, if you put here, it works. So this is alpha plus beta. That's what we did. Now we're going to expand this. This we know how to expand. And to do that, we are going to write this is power to minus alpha minus beta. So this is minus alpha minus beta. And we're going to put pi over 2 with minus alpha together and separate it from minus beta. So we are going to rewrite the brackets in this following manner. So we combine these two and we separate this. And now, since this has a negative sign, cosine of this minus that, we are going to use this. So take a look, we're going to use this formula. We're going to use this formula. It says cosine of the first minus the second will be cosine of the first, cosine of the second. Cosine of power 2 minus alpha times cosine of the beta. And this is a negative sign, so that's why we go with the plus here. Sine of the first one, sine of pi over 2 minus alpha, sine of beta. So according to this formula, we get this one. Now, what is cosine of pi over 2 minus alpha? Sine of alpha. So this is sine alpha. What is sine of pi over 2 minus alpha? Cosine alpha. So this one is sine alpha. This one is cosine alpha. And now we proved sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. In order to prove the second one, so minus b, we are going to write it plus minus b. So alpha minus b, it's alpha plus minus b. So into this formula, alpha is the same. Replace the beta with minus beta. In this formula, replace the beta with minus beta. Cosine of minus beta, cosine is an even function, is itself cosine of beta, but sine is negative minus sine beta. And that is the proof of the second formula. So we established all these identities that we see, starting with cosine of alpha minus beta. We proved the next one, then the next two, and this last. All right, we want to find sine of 19 pi over 12, and we want to cut this into two pieces that are common arc. So what about 16 pi and 3 pi? This becomes 4/3 pi, or 4 pi over 3, and this becomes pi over 4. Both of them are common arcs. Anytime you have a pi and the denominator is 2 or 3 or 4 or 6, those are all common arcs, no matter what the coefficient of the numerator is, any integer by that, I mean. So now we are going to use the first formula, sine of alpha plus beta. So sine of 4 pi over 3 cosine beta, cosine of pi over 4, plus cosine alpha, cosine of 4 pi over 3 sine beta, sine of pi over 4. All right. At first, the pi over 4 cosine and sine are obvious. Both of them are the same, square root of 2 over 2. I want to discuss that. And first, when we have 4 pi over 3, the reference arc is pi over 3, which means this is the same as sine of pi over 3, which is square root of 3 over 2. You figure out the quadrant, it makes it positive or negative. So we know the answer, the numerical value is square root of 3 over 2. We need to figure out positive or negative. This is in the third quadrant. Let me just write it here, quadrant 3, right? Because it's larger than 3 pi over 3, which is pi. In quadrant 3, sine and cosine are both negative. So sine of pi over 3 is square root of 3 over 2. This makes it negative, negative square root of 3 over 2. Cosine of pi over 3 is 1/2. 4 pi over 3 makes it negative 1/2. So in both cases, the denominator is 4. And the product of these two is square root of 6. Put a negative in front. Square root of 2, put a negative in front. And that's the final answer. We want to find the exact answer. So we want to compare this and figure out which one of these formulas. We have cosine, cosine minus sine, sine. So which one is that? Cosine, cosine minus sine, sine clearly is this one. So this is cosine of alpha plus beta. Cosine of 40 plus 80. Which is 120. Cosine of 120 is the same as cosine of 60, which is 1/2. In the second quadrant, cosine is negative, so negative 1/2. So quickly, this one, theta r is 180 minus 120, which is 60 degrees. That's why it's the same as sine of cosine of 60 degrees. In quadrant 2, cosine is negative. This one, we compare it to one of those formulas. Sine alpha cosine beta minus cosine alpha sine beta. So clearly looks like that. Take a look. Take a look at the formula and take a look at the given statement. where alpha is 80, beta is 20 degrees. So this becomes sine of 80 minus 20. So let me write that in case. So this is alpha, this is beta, this is alpha, this is beta. That's the idea. Alpha, beta. And sine of 60 degrees, we know it to be square root of 3/2. We are given sine alpha to be 4/5. And it's between pi/2 and pi, which makes it the second quadrant. Sine beta is minus 2 over square root of 5, or minus 2 square root of 5/5. And it's between pi and 3 pi/2, which makes it the third quadrant. We want to evaluate cosine alpha, cosine beta, cosine of alpha plus beta, sine of alpha plus beta. So I put cosine of alpha plus beta, sine of alpha plus beta here using those formulas that we have. So what we need to do, given sine, find cosine, and we are going to do that for both. And then we figure out the sign, whether it's positive or negative, depending on the quadrant. And again, since this is quadrant, we need to calculate the cosine. So cosine of alpha. And we said this is the second quadrant. And in second quadrant, cosine is negative. We already know that. Okay. And this is the third quadrant. In third quadrant, both of them, sine and cosine, are negative. So we know the sign. But normally we're going to use identity. But I want to remind you also, going back to what we learned, the beginning sign is 4/5. If we go with y over r, y becomes 4, r becomes 5. This is quadrant 2. And you can calculate the x, and it's -3 in the second quadrant. And cosine becomes -3/5. Again, just to remind you of what we did in the beginning when we dealt with the unit circle and then the circle where the radius wasn't 1 but general. However, it's really a better idea to use identities at this point, where sine squared plus cosine squared is 1. Therefore, cosine is plus minus the square root of 1 minus sine squared. Okay. This comes from the fact that sine squared, I want to make sure that everybody remembers that. This comes from the fact that sine squared plus cosine squared is 1. That's where it comes from. So you can calculate the sine, calculate the cosine. It's plus minus. And as we said, because of the quadrant, we are going to keep it as negative. First of all, when you put 4/5 and you square it, you get 16/25. And 1 minus that is 9/25. So it's plus minus 3/5. And in the second quadrant, we take the negative, and we are done with this part. Let's go calculate cosine of beta. So sine is given. We are in the third quadrant. In the third quadrant, sine and cosine are both negative. So cosine is plus minus the square root of 1 minus sine squared beta, again coming from this formula. And so we plug in 2/5 minus 2/5. When you square it, you get 4/5. This, everybody, is 4/5. And 1 minus that is 1/5. So you have the square root of course, plus minus 1/5. So plus minus 1 over the square root of 5, if you take them out, or minus square root of 5/5. Remember, in quadrant 3, it's negative. So what do we have? Let's summarize what we have. because we need to find cosine of alpha plus beta. We need cosine alpha, cosine beta, sine alpha, sine beta. We need all of those values to be able to come up with this. So let's summarize what we have. We had sine alpha to be 4/5. We calculated cosine alpha to become negative 3/5. We had sine beta to be negative 2 square root of 5/5. We calculated cosine beta to be negative square root of 5/5. Now plug in. So I hope you realize that 5 and 5 is 25. So the denominator is 25. These two, negative times negative is positive. You have 3 square root of 5 here. And again, negative times negative is positive. 4 times 2, 8 square root of 5. So the numerator is 3 plus 8, 11 square root of 5. And the denominator is 5 times 5. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. We have the summary here. We're going to plug in. That's the beauty of the summary. It helps us plug in nice and easy. And again, the denominator 5 times 5, 5 times 5. The denominator is 25. This one is minus 4 square root of 5. The other one is plus, minus times minus is plus, 6 square root of 5. They add up to 2 square root of 5 over 25. All right, a quick recap. Sine of alpha and sine of beta are given. We use the formula sine squared plus cosine squared alpha to establish cosine alpha and cosine beta. We summarize them, and we use the sum formula for the cosine of alpha plus beta and sine of alpha plus beta to get to the answer. We want to establish this identity, so most of the time we start from the most complicated side. In this case is the left-hand side, and we're going to expand that. So we get cosine of power to cosine theta minus sine of power to sine theta. As you know, cosine of power 2 is 0. Sine of power 2 is 1. So this goes to 0. This becomes minus sine theta, and that's a proof. We want to prove this. We start from the left side, and we use cosine of alpha plus beta formula. So cosine pi, cosine theta, minus sine pi sine theta. We are looking at the left-hand side. We know cosine pi is negative 1, and we know sine pi is 0. So this goes away. This becomes negative cosine theta, and that's a proof. So we establish the identity. We know sine and cosine here. We want to prove tan of alpha plus beta is tan of alpha plus tan beta over 1 minus tan alpha tan beta. So we want to prove the first one, and we know tangent, so we want to prove this. These are the formulas we were discussing at the beginning when I gave you the summary. How do you prove that? You start with the left-hand side and you say tan is sine over cosine. So sine of alpha plus beta over cosine of alpha plus beta. Now you write sine of alpha plus beta at top. You write cosine of alpha plus beta at the bottom. Now, we can look at back the formula. Look back at the formula. Look back at the formula. This is 1. That means somehow we want this to become 1. That gives us a hint, which is, what if we divide everything by this? Again, take a look. This is 1. How do we make this one 1? If we divide by cosine alpha, cosine beta, this becomes 1. So that may give us the answer. So let's divide everything by that. We are dividing everything by cosine alpha, cosine beta. In the numerator, we make up 2 fractions. In the denominator, we make up 2 fractions. And now we simplify. This one cancels out this one. This one cancels out this one. This whole thing cancels out this whole thing, which gives us 1. So let's see what we have now. We use a different color. We have this one, sine alpha over cosine alpha is tan alpha. We have this one. Maybe I use a different color for that. Sine beta over cosine beta is tan beta. Sine alpha over cosine alpha, we replace it with tan alpha. Sine beta over cosine beta is tan beta. And that's what we get. And that's a proof. So we proved the first one. I'm going to leave it for you to prove the second one. And here's the hint. All you have to do, say you're going to replace the b with minus b. So write down alpha plus negative beta. And establish this, replace every beta with negative beta, and you get to the second one. So again, write down alpha plus, so here's the way to do it. Write tan of alpha plus negative beta, and just the way we did it before for sine and cosine, you can easily come up with the answer. All right, we want to establish this. Tan of 2 pi minus theta is minus tan theta. We are going to look at the left-hand side, and this is alpha minus beta. So we're going to use alpha minus beta. So tan of alpha, that means tan of 2 pi, minus tan of beta, that means tan of theta, over 1 plus tan alpha tan beta, tan 2 pi tan theta. So we use the first one. We use this formula. As you know, tan of 2 pi is 0. Let's replace it with 0. And therefore, the top becomes minus tangent theta and the bottom becomes just 1. And we proved it. Minus tan theta. We are done. We want to prove cosine of alpha minus beta over sine alpha sine beta is cotangent alpha cotangent beta plus 1. By the way, you can establish cotangent of alpha plus beta by writing it as 1 over tan of alpha plus beta and establish. In any event, we look at the left-hand side, cosine of alpha minus beta over sine alpha sine beta, and cosine of alpha minus beta, we use this one. So here's the left side. And the top, we're going to use this formula, cosine alpha cosine beta plus sine alpha sine beta. All we have to do, make up two fractions. This is one, and this is another one. So we cut this into two fractions. So clearly this is 1 because the top and the bottom are identical. Cosine alpha over sine alpha is cotangent alpha. Cosine beta over sine beta, it's cotangent beta, and that's a proof. We want to prove tan of tangent, tan of theta plus power 2 is cotangent theta. And there are a couple of different ways. You can go with the sum formula for tangent and explore that. We can also write tangent is sine over cosine. So the left-hand side, tan becomes sine of theta plus power 2 over cosine of theta plus power 2, and we're going to expand it. For the sine, we use sine of alpha plus beta, which becomes sine theta cosine power 2 plus cosine theta sine power 2. And for cosine of theta plus power 2, we're going to write cosine theta cosine power 2 minus sine theta sine power 2. So we're going to use those formulas. And we know that cosine of power 2 is 0. Sine of power 2 is 1. We're going to replace it. Cosine of power 2 is 0. Sine of power 2 is 1. So this is 0. This is 0. We are left with cosine over negative sine. And that is cotangent theta. That is negative. Let's make sure this is correct. So sine theta cosine power 2, cosine theta sine power 2. Oh, that's not sine. Theta times cosine power 2, that is 0, plus cosine theta sine power 2. And the bottom one is cosine theta cosine power 2 minus sine. So this must be minus cotangent. So it's minus cotangent. beta. That's the establishment. All right. Let's establish this identity where cosine of alpha plus beta over cosine of alpha minus beta becomes 1 minus tan alpha tan beta over 1 plus tan alpha tan beta. And we can start with the left side. For left side, and for cosine of alpha plus beta, we put this. For cosine of alpha minus beta, we put that. Again, we want to have 1 here, so it's easy to see that the trick would be to divide by this one, everything. So there are 2 pieces at top, 2 pieces at the bottom. Everything will be divided by cosine alpha, cosine beta. Clearly, this one is 1, this one is 1. Let's separate this into sine alpha over cosine alpha, sine beta over cosine beta, and so on and so forth. So the first piece is 1. This one we write it as sine over cosine. This one we write as sine over cosine. The same thing here. The reason we separate them because this, this is tan of alpha. This is tan of beta. And we're done. We want to find the exact value of cosine inverse of 2/3, sine inverse of negative 3/4. And remember, each one of these represents an angle or arc. So we can call this alpha, we can call this beta. Therefore, we are looking for cosine of alpha plus beta. And for cosine of alpha plus beta, we need to find cosine alpha, cosine beta, sine alpha, sine beta. And that's exactly what we are going to do. And we plug in. So let's start with this. Cosine of this means cosine inverse of 2/3 is alpha. Cosine of alpha is 2/3. And we are in the first quadrant because it's positive. Remember the inverse functions, they have precisely a unique answer. In this case, sine beta is negative 3/4. And sine, because we go from negative power 2 to power 2, must be in the fourth quadrant, negative power 2 to 0. So we established the quadrants. Okay, so all right. So from cosine, we are going to go to sine. Sine squared plus cosine squared equals 1. Sine is the square root of 1 minus cosine squared alpha, 1 minus 2/3 to the second power. This is a 4/9. So remains 5/9 or square root of 5/3. So that's sine alpha. We do the same thing for the beta. Sine squared plus cosine squared is 1. We plug in, and this is 9/16. 7/16 remains. 1 minus 9/16 is 7/16. And that's the square root of 7/4. So again, in the first quadrant, everything is positive. In the fourth quadrant, cosine becomes positive. Now let's put it into this. We have everything we want. Again, the summary. Sine alpha was given. Cosine alpha was given to be 2/3. Sine alpha was found to be square root of 5/3. Sine beta was given Cosine beta was found to be square root of 7/4. Plug in. When we plug in, clearly the denominator is 12 in both cases. This is 2 square root of 7. This is minus and minus plus 3 square root of 5. And that's a precise answer. I'm going to look at one more example. We want to establish secant of alpha plus beta is secant alpha secant beta over 1 plus tan alpha, tan of alpha plus beta, and we're going to use that starting with secant and knowing that the secant is 1 over cosine. That's why we're going to use that. Secant left side is 1 over cosine, and therefore it makes it 1 over this cosine alpha cosine beta plus sine alpha sine beta. Now, when we want to continue, we look at what we are trying to prove. We're going to get to the right side. So we want this one to be 1. So if we divide everything by this, this becomes 1. Maybe we establish what we want. So look at this one. This is the key. How do we make this one 1? Divide by it. So we divide everything by cosine alpha, cosine beta, and we separate them so it becomes clear what we have. So understand that we just divided by cosine alpha, cosine beta. When we separate them in this format, 1 over cosine alpha is secant alpha, 1 over cosine beta is secant beta. This is 1. And this is tan alpha, tan beta. This is supposed to be tan alpha, tan beta. This is tan alpha. This is tan beta. So there was a typo there. I just fixed it.